corresponding to decrease in some region, but keeping the total probability intact. Keeping the total probability intact. So density we have found for a few of the cases. The first case we have found it for, I think, for the plane wave, that is a e की power iota kx, and we found that this probability density is equals to velocity times modulus of a whole square. If you remember, this is something that we have already done. Second case we've taken for spherical wave function, you can say right now. And we found that if a spherical wave function psi x is given by a e की power iota kr upon r, then this particular thing, this j is equals to, I think it was something like velocity into modulus a square divided by r square. If you can just confirm it, yesterday if somebody was seeing all these things, then is that clear till now? Okay. Now, if I want to find, let us say, okay, the third thing we've seen that the dimensions of probability density was inverse of time. If you remember, yesterday we did this also. One upon time. Okay. Now, what if, just a question I'm giving you, what if we have, let us say, superposition of two plane waves. What if we have superposition of two plane waves? What if we have superposition of two plane waves? That is, let's say, I'm saying that if psi x is given by psi x is equals to, let's say, a e की power iota kx plus b e की power of minus, let's say, iota kx. Okay, so let us say this is your wave function, and then we want to find the current density. So let's say I'm interested in finding the magnitude of it. So what it is equals to, it is equals to h ket upon m, and then I'll find the imaginary part of psi star into grad of psi. Okay, and if I want to find this, I already know this psi. What would be psi star? Psi star would be a star e की power minus iota kx plus b star e की power iota kx. Fine. And what would be del psi upon del x? Del psi upon del x would be iota k a e की power iota kx minus iota k b e की power minus iota kx. Fine. And if I multiply both of them, what I'll get? I'll get h ket upon m. This is imaginary. Psi star into this. So what you'll get? You'll get iota k modulus of a whole square, and then I think there would be minus iota k modulus of b square. So this is iota is accompanied by both. So your probability density would be h ket k upon m modulus of a whole square minus modulus of b whole square. Okay, is that clear? Okay, so this sums up most of our things in probability density. Then a few of the things are left. We'll see all those things later. Now let us discuss something about Schrödinger equation. Let us discuss something about Schrödinger equation. So till now we have seen so far we have seen a Schrödinger equation where we have written it in this form. Today we are going to see time independent Schrödinger equation. Okay, so till now we have seen that Schrödinger equation has been written this way. Okay, now we want to find that if my you can say if I'm considering a potential which is mostly independent of time, that is, if I consider, I'm writing it here, if I consider that my potential is independent of time, independent of time, then can I obtain my, and also that psi is a function of x and t, can I obtain this from this differential equation? After all, we in the entire syllabus we'll be interested in this only, that we'll be given some potential, and according to this potential we want to find what is the wave function like, or what are the eigenfunctions. Okay, so why I'm saying eigenfunction, because when we'll solve this we'll find that we are going to get an eigenvalue equation. Okay, so we want to see this. So what is way ahead? You know that this is a kind of partial differential equation in front of you. And you know, one of the methods to solve this partial differential equation is to use the separation of variables. Okay, so is to use separation of variables, and we write psi. Uh, Basically, I'll write it as some capital psi. Okay, so I'll use this way, some capital psi, otherwise you'll get confused. So okay, this capital psi as a function of x comma t, I can write psi as a function of x times some phi you can take phi as a function. Okay, and now if you just see this, so what we'll get, so if I differentiate this, because this is a function of t, this is a function of x. Okay, and if I place all these things, also this one, it will be equals to del square. Okay, so this is one thing. If I replace all these things in the above equation, if I replace all these things in the above equation, what will I get? So I will get one thing, that is iota h ket, and then psi, then you'll have del phi upon del t here. Okay, is equal to minus of h ket square upon twice m, and then you will have del square psi upon del x square phi plus v psi into phi. And what we do usually, we actually divide it. So we'll divide it throughout. So if I divide it, what I'll get iota h ket upon 1 upon phi del phi upon del t. And if I divide it here also, what I'll get minus h ket square upon twice m, 1 upon psi I will get. And then I will get, I think, v. Okay. Now what happens is that this side, if you see this particular side on the left-hand side is a function of t, and this particular side on the left hand, if I'm not saying that v is, if I've already taken v is not a function of time, so overall this particular side is a function of x. So it may so happen only if both of them individually are equal to some constant. So I'm writing, it may so happen that both of these sides are individually equals to some constant, and let us keep that constant equals to e. So iota h ket 1 upon phi del phi upon del t is equals to, let's say, e. And here also I'm going to write the same, minus h ket square upon twice m, 1 upon psi del square psi upon del x square plus v is equals to e. Okay, so there Okay, sorry. So I'll write this as minus e. I'll write this as plus e. Fine. This will put your sign in consistency. If I'm placing this as e, so this will be minus. Okay, is that clear? Till now things are clear to you. Don't worry, if you're not getting probability current density, I'll help you out someday. Okay, I'm not able to explain it in a very lucid manner, but overall, uh, this is how it is like. So if this is the case, I know if I this if I integrate with respect to t only, so I know del phi upon del t. This integrate will give you this integral will give you ln phi, and you take all those things there, so you'll get phi as a function of time. I think you'll get some e ki power of iota e t upon h kit. Okay, and I'm going to absorb c in this particular psi only, so don't worry. So there would be some constant indeed, but psi will also be accompanied by some constant only. So overall, we'll see that we'll see it there. Is that clear? Okay, good. So and this particular thing here, this particular thing that is minus h kit square upon twice m, take psi there. So it is del square psi upon del x square plus b psi is equal to e psi. This is referred to as your time independent Schrödinger equation. So, and it so happens that if you want to write it in operator form, it is h ket psi is equal to e psi. Your h ket is the operator corresponding to the observable. So if you closely observe, this operator is this way I can write. So basically h ket psi is equal to e psi. It so happens that it follows a eigenvalue equation, and this particular thing is called as your time independent Schrödinger equation. Is that clear? Okay.
Yes, sir.
Okay, good. This is one thing. So let us, yesterday also read a few questions. Today we are going to repeat those questions because I think that did not get recorded or something. Okay, so just start from a simple question and then I'll take you to a difficult question. So let us say that you have this kind of thing. Okay, so let us say you have this kind of this kind of one-dimensional wave function, that is psi x is given by a times x by x naught raised to power n e raised to power minus of x by x naught. Okay, where here a, n, and x naught are some constants. They are some constants. We want to find. We want to find v as a function of x, v as a function of x, and energy E, for which this wave function is an eigenfunction. Eigenfunction of what? Eigenfunction of the time independent Schrödinger equation. We assume that the potential so behaves that as x tends to infinity, your Vx tends to 0. Now, how would you approach this question? So clearly, this wave function is not time dependent. We're going to use the time independent Schrödinger equation. Okay, so how we are going to do? Yesterday also we did this question, but somehow there was a problem. Okay, so this is one. How would I do? I'll take this derivative at first. So the derivative will be a n upon x naught, x by x naught raised to power of n minus of 1. And then you have this e raised to power minus of x by x naught. And then you'll have this plus a. I think x by x naught remains as it is. Raised to power n remains as it is. And you'll get minus 1 upon x naught into e raised to power of minus of x upon x naught. What would be the second derivative of the same? The second derivative of the same would be a times n into n minus 1. This x naught will come outside, so you'll have this x naught whole square. And then you have this x minus x naught raised to power of n minus of 2. Then e raised to power minus of x by x naught. One derivative, this also will differentiate. And if I differentiate this all over again with respect to like if I take the derivative of e की power, I'll get this x naught square. So I'm going to write it first. This is a upon x naught whole square, x by x naught raised to power n, and e की power minus x by x naught. And then there would be middle term, and the middle term will be same here and here as well. So you just see, if you differentiate this, you're going to get what? You're going to get minus of a, and there would be some n also, x naught whole square, x by x naught raised to power n minus 1, and then you will get e की power of minus of x by x naught. Is that clear? And from here also you'll get the same. See, if I differentiate this, n will come up outside, this n minus 1 will appear, and this x naught will come here. So x naught, x naught, x naught square. So I'm going to write 2. So this is the second derivative. So if I want to a little bit arrange before going further, if I arrange this up, so if I take this x by x naught raised to power n common out, so I'll take x by x naught raised to power n common out, and e की power minus x upon x naught also common out. So remaining terms you see. If I see the remaining terms, this will be n into n minus 1. This x naught square and this x naught raised to power minus 2 would get cancelled, and you will be left with only this x squared minus of 2n upon x naught into x plus 1 upon x naught whole square. I think this is clear. I don't think there is a mistake. Just see if there is a mistake. Otherwise, we'll do something wrong. Okay. And now I'm going to apply this minus hk square upon twice m d square psi upon dx square plus vx psi, right? Vx psi should be equal to e psi. Now, if you think what you're going to get from here, you know that this is your psi. So your psi is getting repeated. So I'll write minus hk square upon twice m. Then n into n minus 1 upon x square minus 2n, sorry, minus of 2n upon x naught into x. Then I will have plus 1 upon x naught square, right? And plus Vx, and you have this E psi. Now, already we know that, sorry, this psi will also remain. So I'll write psi here, psi here. Now, we already know that as x tends to infinity, your psi x goes to 0. Sorry, your Vx goes to 0. Your Vx goes to 0. Which implies what? As x tends to infinity, this would go to 0, this would go to 0. So your total energy E is equals to minus of hk square upon twice m x naught square. Is that clear? And if I use this here, I'll get the potential also. Your potential will remain only this. So this is like, already we know that Vx plus this particular thing is equal to E. E I already know, and this entire thing will go there. So I'll get hk square upon twice m. n into n minus 1 upon x square minus 2n upon x naught into x. I hope it is clear till now. So this is your Vx. Okay, is that fine?
Yes.
Okay, so this is one thing that I wanted to teach. Now, I'll give you one more question. Okay, so a few questions on normalizations and simple questions so that you'll be able to gain some sort of confidence. We've already done expectation values. So I'll give you directly some questions regarding expectation values also. Try to do them. Okay, so let us take some easier example at first. Let us take some Gaussian wave function, and from there we'll take it at little bit difficult also. We'll see some difficult questions also later. Okay, try to do a simple question. Consider a Gaussian wave function. Consider a Gaussian wave function, and let us say I write this fashion: psi x is equal to some constant t, a raised to power minus lambda x minus a whole square. We want to normalize it, so we want to find what would be your a. We want to find the normalization constant a. We want to find normalization constant a. Okay, try to find the normalization constant a. It's easy. And some integrations that may be useful to you, I'll write it here so that whenever you are doing it. So if I want to write 0 to infinity, this integration, just remember this. You can find it also using gamma function, but instead of finding time and again, I'm going to write it for you so that you don't get confused. Okay, so if I want to find the normalization constant, things are very easy. You know, it is minus infinity to plus infinity psi modulus whole square dx equals to 1. By the way, how the graph would be, let's say if lambda is positive, because if lambda is negative, then this will not be a swell integral function. So lambda must be positive. Even if it was not given, you have to understand this, that lambda should be positive. Otherwise, it will blow as x tends to infinity. And instead of Gaussian at x equal to 0, this will be Gaussian at x equal to a. And a also let us take as positive only. So instead of Gaussian at x equal to 0, it will be Gaussian at x equal to a. Okay, so this is how your Gaussian graph would be. This is a times e to the power of minus lambda x minus a whole square. Okay, and what would be this? From here you can find that your A modulus full square would be minus, e to the power of minus 2 lambda. Is that fine? Somebody say something else. Okay, so this will be like A mod whole square minus infinity to plus infinity e raised to power, and you just take x minus a as some u. So your dx will be du. So you will write this du here, and this will be e to the power minus 2 lambda u square. From this particular expression, try to find this. So you know that already that 0 to infinity, if e to the power minus of x square dx you are trying to find, it is equal to 1 upon 2, and then you have this root over pi upon a, and if it is minus infinity to plus infinity, 2 vanishes. So basically it is mod a whole square. So these are quite routine questions, but don't make mistake in these questions, okay? So a comes out to be equals to what? A comes out to be 2 root over raised to power 1. Is that fine?
Yes.
Yes, these are easy questions. Now try to find some expectation values also. So let us say that
सर 1/2 कैसे आया वो?
not 1/2, sorry. Okay, so this is not right because minus infinity to plus infinity, if you write, then this will vanish away. So this will be root over pi. Okay. So now let us do a question here. So let us say that your wave function psi at time t equal to 0 is given by let's say 3 portions. I'm giving you. The first is ax upon a. Here x lies between 0 and a, and when x lies between a to b, it is equals to a times b minus x divided by b minus of a, and otherwise it is equals to 0. Otherwise it is equal to what? 0. Here a, b, and these are some real constants. That is, you want to find the value of a in terms of a and b. The first question. Try to find the value of a and b in terms of your small a and small b. So how would you do that? See, first let us try to sketch this particular wave function. So how this particular wave function behaves? So from x equal to 0 to a, it behaves linearly. From x equal to 0 to a, it behaves linearly. At x equal to a to b, and from x equal to a to b, it is a decreasing function, c minus of x. And at x equal to b, it will be 0, and then throughout it would be 0. Okay, throughout it would be 0. Is that fine? So this is how you can plot your wave function. Now we want to find the value of a in terms of a and b. So how can we find that? Let me try to integrate this. So I already know that, what do I know? That psi mod whole square dx from minus infinity to plus infinity, it should be equals to what? 1. So total probability of finding the particle anywhere in the space should be equal to what? 1. So if that's the case, what I'll do, I'm going to find it from 0 to a. I already know that this is a real function. No? So even if I take a star in this, so it's going to be, I'm going to write it here. This is a mod whole square divided by a square, and then you are left with this x square dx. Plus, again, this a is there. So here this a would become a mod whole square divided by b minus a whole square. And then you will have this thing, integration from a to b. See, minus infinity to 0, your wave function is 0. From b to infinity, again it is 0. But here your wave function is there. So here you will have b minus x whole square dx. This entire thing is equals to what? 1. And if you find this, what you're going to get? You're going to get a mod whole square divided by a square into a cube by 3 plus 1 upon b minus a whole square, and then you will get this a mod whole square here, and integration of this would be b minus x ka whole cube divided by minus of 3. Please remember this remains. So instead of writing minus of 3, I will change the limits. Okay, so if I change these limits, if I place this, I'm going to get a mod whole square. This is a by 3 plus 1 upon b minus a whole square into b minus a whole cube divided by 3 equals to 1. And from here you'll get a mod whole square. This is a upon 3 plus this gets cancelled. I think you're going to get only b minus a upon 3 equals to 1. From here I get a mod whole square is equal to 3 upon b. Your mod a would be equals to, I think, root over 3 upon b. Is that fine? This is what everybody is getting.
Yes, sir.
Okay, these are easy questions, but we have to do it anyhow. Okay. From the graph itself, so from the graph itself, you can see that it is peaking at x equal to 1, x equal to a. So it has a peak at x equal to a. And you should remember that uh, it is having a peak at x equal to a. So the maximum likeliness to find the particle would be at x equal to a. So your particle would, if particle whose wave function is this, the maximum likelihood is to find it here. Is that fine?
Yes.
Okay, good. Now we want to check the probability. These are very easy questions, but fine. We want to check the probability of finding the particle to the left of it. Okay. What is the probability of finding the particle to the left of A? Left of A means from 0 to A. So that would be equal to what? Integration from 0 to A psi mod whole square dx. And we already know this A mod whole square now. So this will be, I think, 3 upon B integration from 0 to A x square upon A square dx. Now try to find this.
A by B.
Okay, so this will be a by b. Try to find the expectation value of x. So what is the expectation value of x? And if you don't know expectation value, I'm going to write it this way. It is x size x. So x remains x. So it will be x mod whole square dx simply. Because psi star x psi, or whether you write this or you directly write this, because they're one and the same thing. So this is equals to what? This is equals to the expectation value of x. Try to find this result. What this would be? What do you think the expectation value of x would be?
3a स्क्वायर बाई 4b.
हाँ बेटा,
3a स्क्वायर बाई 4b होगा सर.
नहीं, कुछ और आंसर आ रहा है. Just try to find it. What is the expectation value of x? Okay, it's not this only. I'm not saying expectation value of x to the left. I'm saying expectation value in general. So what would be expectation value? So expectation value of x would be x psi mod whole square dx. It would be equals to what? It would be equals to, I think, mod a whole square will come here. I already know mod a whole square, so why keep writing it time and again? Directly write it as 3 by b. So I'll write it as 3 upon b. Inside, from 0 to a, the value is, I think, a square x square upon a square plus from a to b. What is that wave function? Where it has come? So wave function is, so it is b minus x whole square. I think there should one more x should come. So this will be x cube. One more x will come here, and this will be like b minus of a whole square. And then there would come dx here. I think it is clear. And from here, if you want to find, you can find 3 upon b. And this integration would give you what? This integration would give you 1 upon a square here. A की power 4 by 4 is here. Plus 1 upon b minus a whole square is here. And from here, you have to expand it. I think b square and b square x. So you'll get b square x square by 2. Then plus x square into x cube. So you'll get x की power 4 upon 4 minus 2b x square. So you'll get minus 2b x cubed by 3 from a to b. So finally, you'll get, I think, 3 upon b is here. You'll get a square upon 4 plus place b here. So you'll get 1 upon b minus a whole square. And then you'll get, I think, b की power 4 upon 2 plus b की power 4 upon 4 minus 2b power 4 upon 3. Okay, then you have to place a also, right? Okay, so this 3 by b is common everywhere, right? You don't have to make mistake, otherwise we are gone then. Okay, if I place this minus of b square by 2 minus of a की power 4 by 4 plus 2 a cube b upon 3. So expectation value of x would be equals to this entire thing. You have to solve this particular thing. So kindly solve this particular thing. So one thing I can take this common, right? So if I take this common, and in fact take this 4 also common. So let me take 3 common is there, b is common is there, take 4 also common, and take b minus a whole square common. So you are now going to get a square into b minus a whole square, and plus 4 will go there. So you'll get 2b की power 4. Okay, this is what not even 2 b की power 4, so add it up. So this is b की power 4, b की power 4 plus b की power 4, and add it. This is 3b की power 4 plus 2. This is b की power, this particular thing is b की power 4 upon 12. And if 4 comes there, so you'll get, I think 3, sorry, you'll get b की power 4 upon 3, b की power 4 upon 3, and then minus of 4 will come here, so this will be like minus 2a square b square. 4 will come here, so minus a की power 4. 4 will come here, so this will be plus 8 a cube b upon 3. Is that fine till now? I think this is quite easy. So this is expectation value of x would be 3 upon 4b, b minus a whole square. From here you get a square b square plus a की power 4 minus 2 a cube b plus b power 4 upon 3. I think this would be 2. Okay, so this gets cancelled. Minus 2a square b square minus a की power 4 will also get cancelled. Okay, so a की power 4 gets cancelled. Minus 2a square b square also get cancelled. And minus 2a cube b. So 6. So this will be, I think, expectation value of x would be 3 upon 4b, b minus a whole square. And you are left with, I think, 2 a cube b upon 3, because this would be 6. 8 minus 6 is 2, 2 upon 3, plus b की power 4 upon 3. Okay, no, this is not. So a square b square here. So minus a square b square will still remain. Sorry. So minus a square b square will still remain. So this is 2, this is 1. Fine. So this is final, I think. Everybody has got this answer. You can take, I think, 3 common from here. So if you take 3 common, you'll get 1 upon 4b, b minus a whole square. You take 3 common, so you'll get 2a cube b plus b की power 4 minus 3a square b square. It's not a square b square also. How to solve this? Try to solve this. 1 upon 4b, b minus a whole square. What you'll get out of this? So I think this is b square Yes, I'm leaving it here only. Okay, so you just can solve it beyond. I think there's some problem with water. If I take b also common, so b gets common, so this will not remain, this will not remain, this will not remain. So after all, I'll get 1 upon 4 b minus a whole square, and this is, I think, b cube minus 3a square b plus 2a cube. This is what I'm getting at the end. So this is the expectation value of x. It is equal to 1 upon 4 b minus a whole square, and then you have this b cube minus 3a square b, and then plus 2a cube. If you can solve it further, you can also I think do it. Okay, I think we can solve it further also. It's a long question. Okay, so b minus a whole square. This particular thing b cube minus a square b minus 2a square b plus 2a cube. I think now I can write it as 4b minus a whole square. If I take b common from here, so I'll get b square minus of a square. And if I take minus of 2a square common from here, it is b minus of a. I think it is fine now. So if I take overall b minus a common, what am I going to get? I'm going to get 4 times b minus a, and here I'll get b plus a into b minus 2a square. And from here also I'm going to get 4 times b minus a. This is b square plus ab minus 2a square. Again it is ठीक है जो है जो at the end I think this will be 1 upon 4 b minus a, and then this is b square plus ab minus a square here, and again minus a square. Okay, from here again take b minus a. So this will be b plus a plus a. So this gets cancelled. So we'll get 2a plus b upon 4. Is that fine? So this is your expectation value of x. Just a lengthy question, but fine. Good for initial practices. Okay, is that fine? Should I go ahead?
Yes.
Okay, good enough. एक और देखते हैं. Let us do one more question. Simple questions. I think these questions you will practice on your own, but today was the first class, so I thought, why not do it today itself? Okay. So try to find this. Let's say a particle is represented by the wave function psi x is equal to e की power of minus of modulus of x sine of alpha x. We want to find the probability that its position is to the right of x equal to 1. We want to find the probability such that its position is to the right of 1. Okay. First, always whenever there is a modulus there now, so always define it at first. Always remember modulus is equals to x if x is positive, and it is equals to minus of x if x is negative. So psi of x is equals to e to the power of minus x sine of alpha x when x is positive, and it is equals to e to the power of x sine of alpha x if x is negative. So we want to see to the right of x equal to 1. So x equal to 1 is positive. So this is the wave function. Sorry, this is the wave function that you should consider. Is that fine? Yes or no till now? Always remember, this is something usually people do a mistake here. Always normalize the wave function if it is not normalized. Always normalize the wave function if it is not normalized at first. If it is not normalized. So first try to normalize the wave function. Okay, is that clear? So if I normalize this wave function, how will I do? I know this is psi mod whole square dx integration from minus infinity to plus infinity, and I know from minus infinity to 0, the wave function is this. So I'll simply write the square of this because this is real. So e to power 2x sine square alpha x dx, and from 0 to infinity e to power of minus of 2x sine square alpha x dx. Okay, is that fine? And you can take even negative common from here. So if you take x equal to minus x, if you take x is equal to, one thing you can do, one thing easier you can do. What I can do is I can write it as minus infinity to 0 e to power 2x, and then I can write 1 minus of cos 2 alpha x divided by 2 dx. Fine. And here also I can do the same, e to power minus 2x, and this would be 1 minus cos 2 alpha x divided by 2 dx. Fine. And let us take all these things here. So, so this will be minus infinity to 0 e to power 2x divided by 2 dx plus integration 0 to infinity e to power minus 2x divided by 2 dx. And then think about this. It is negative is there. So I'll take this negative, absorb this negative, and I'll repeat this limit 0 to infinity e to power 2x cos 2 alpha x dx. And then another term is from 0 to infinity e to power of minus 2x, and there is a negative minus 2 alpha x dx. Okay. Try to do this from here. I think it is easy. You can do these from the, even if you have some knowledge of Laplace transform, otherwise you'll have to go for that in the, like you will have to find it using uh, integration by parts. So if you know Laplace transform, it is good. If you don't know the Laplace transform, then you'll have to find it using uh, what you can say by integration, normal integration. Even in Laplace transform, we actually do integration, but usually in Laplace transform, we know some standard Laplace transforms. So that way it becomes easy for us. Try to do this. I'll write if somebody does not know this. So Laplace transform of, I think, the cos of omega t. It is equals to integration from 0 to infinity e to power of minus of st cos of omega t dt. It is equal to, I think, s upon s square plus omega square. So you can do it by comparison. Okay, you can do it by comparison. So you know that this psi mod whole square dx would be equals to 1. So it would be equals to 1. So I'll write 1 here. What this integration would be? This integration would be e to power 2x by 2 is also there, right? Okay, by 2 is also there. So this would be 1 by 4 here, and e to power minus 2x divided by minus 2. So minus 1 by 4. I'll revert the limit. So again, it is plus 1 by 4 minus this integration. This integration would be what? Instead of s, you have 2 here. So I'll write 2 divided by 4 plus 4 alpha square. Right? Is that clear? Why is there a mistake somewhere? So e to the power 2x minus was the, acha, it is, okay, it is from minus infinity. So it is 0 to minus infinity. So sorry. So if it is minus infinity, 0 to minus infinity, how will you be able to place? So what I can do, I can write x is equal to minus t here. So if I use x equal to minus t, so this will be e to the power of minus 2t. Cos is an even function, fine. Dx would be minus dt. So negative will come outside from 0 to plus infinity. Is that fine? Now from here you can do, right? From here you can apply this Laplace transform, or just use it as a formula right now if you don't know Laplace transform. I think this will be like in minus of 2 divided by 4 into 1 plus alpha square. Is that fine? Or is there something else also? Okay, there is by 2 also is there. Okay, so there is by 2 also is here. So 1 by 2 is here, 1 by 2 is here. So overall, this will become, I think, by 2 is here. So this negative I'll take common out. This 1 by 2, 1 by 2. Okay, so eventually what you are going to get, this 1 by 4 plus 1 by 4 will give you 1 by 2. Take 1 by 2 there. And we have not multiplied it using some constant. So I should have multiplied it using some constant. So multiplied using some constant. So take normalization constant to be equal to a. So it will be modulus of a whole square here, modulus of a whole square here, modulus of a whole square here, modulus of a whole square here as well. In the entirety, you take a modulus of a square here also. And then here also modulus of a square. So I'll take a modulus of a square. Okay, so now just tell me what will be the answer. What would be the normalizing constant? So 1 upon modulus of a square would be equals to what? 1 upon 2 minus of 1 upon 2 gets cancelled. So this is 2 upon 4 1 plus alpha square, right? And this will give you what? This will give you 4 1 plus alpha square minus 4 divided by, even if I take this out. There's a minus here, no? So
अल्फा स्क्वायर बाय 2 into 1 plus अल्फा स्क्वायर आ रहा है.
हाँ से कुछ राइट. So इसको हटा ही देते हैं, गलती हो गई. एक मिनट. So I think this is fine and this is fine. So ultimately कितना रहा? 1 upon alpha a mod square 1 by 2 कॉमन ले लो यहाँ से देखो 1 minus of 1 upon alpha square. So it is alpha square upon 2 1 plus alpha square. ये आ रहा है ना? This is what you are getting. So mod of
Yes, sir.
a is equal to root over. So these are lengthy questions, first day of questions. So I gave you all these questions. So tomorrow we are going to take some good questions from exam. Okay, so this is part of it. Now we have to find the probability of finding the particle to the right of x equal to 1. So what we have to, first let us write our wave function. So a wave function for all x greater than 0 will be equals to what? This entire normalizing constant, which is 2 into 1 plus alpha square divided by alpha square e to power minus of x, and then sine, it's modulus, but for all x greater than 0, I'm writing sine of alpha x. Okay. Now try to find what is the probability of finding the particle to the right of x equal to 1. So it is from 1 to infinity, and psi mod whole square dx, which will be equal to writing 2 times 1 plus alpha square upon alpha square, because after all this is real only, so basically it would be like mod of whole square, integration from 1 to infinity e to power of minus 2x, and then sine square alpha x dx. Now we have no other options than to integrate it, because now this is not 0 to infinity. Now this is from, uh, unfortunately, it is from 1 to infinity. So we'll have to use it. We'll have to find it using what you can say, integration by parts. We'll have to do integration by parts here. Okay, so this is, I'm leaving up to you. I'm directly writing the answer. The probability, you just have to confirm this is equal to e to power of minus 2 divided by 4 times 1 plus alpha square and then you have this 1 plus alpha square minus of cos 2 alpha plus alpha sine 2. So this is your probability. You just have to find it. I think you'll be able to find it on your own. Just try to integration. I'm writing it here. Try to integrate by parts, because there is no other way out. Now you cannot use the Laplace transform here. Is that clear? So we'll meet tomorrow, and I'll try to figure out your doubt also, Deepta. Okay, so you send me those doubts and I'll see those doubts. Okay, but
Okay,
overall,
sir.
overall I feel it is good. It is fine. ये सब हो जाएगा.